Algebra 1, Lesson 120. We are looking at probability of event, but in this case, using a little bit of geometry in order to find that probability. So, for this, theoretical probability, remember, is just the ratio of favorable outcomes to the total number of outcomes. This same idea applies when we are talking about geometry, but instead of talking about outcomes, we're talking about typically an area, a space that you are saying is the biggest possible area that you're trying to hit, and the favorable outcomes is basically trying to fit inside of that, hit like the bullseye on a piece, whatever it might be. Okay, so easiest way to explain this is really just showing examples, and that's what all of this lesson will be just a bunch of different examples of geometric probability. A rectangular vegetable garden is 10 feet by 15 feet. So we have this vegetable garden, 10 feet by 15 feet. Tomatoes are planted in a rectangular area that is 3 feet by 12 feet. So let's say here's our 3 feet by 12 feet. A bird lands in the garden. What's the probability that it lands in the tomato area? Well, just like regular probability, we need to figure out what is our total number of outcomes. In this case, what is our total number of feet that the bird has for landing in? And we would say the total area would be the big rectangle, the entire garden. We know it lands in there. That's our total number of outcomes or area. So we would say the area of that is 10 times 15 or 150 feet squared. Well, we want a certain outcome. We want him to land in this spot that grows tomatoes. That's 3 by 12. Well, that would be our numerator. Just like we would say, I want the number 2 on a number cube, and that's one outcome out of 6. Here we're saying there's 36 square feet that he can land in to be successful out of a total 150 feet. So from here we can reduce a little bit. We can say, let's see, reduce by, let's just start with 2. So we have 18 over 75. And let's see, that can be reduced again by 3s to get 6 out of 25. Okay, so it's a 6/25 chance in order for the bird to land in that tomato area of the garden. Let's try it again. A sheet of paper 12 inches by 9 inches is lying on a table. The table is 15 inches by 18 inches. Okay, so then we have this smaller piece of paper in here that's 9 inches by 12 inches. What's the probability that a fly will land on the paper if it lands on the table? Well, we can say the total area of the table is our total outcome, so 15 by 18. So 15 times 18 gives me 270 square inches, and then we would say the area of this piece of paper inside of that is what we want him to land into. Okay, or for another example, this is like if I had a bunch of marbles in a bag and I know 5 of them are blue, then those 5 are like the area of landing on that piece of paper. Those are the ones that I want. So I would say in this case 9 times 12 is 108 inches squared, and then you can reduce from there. Let's see, you can reduce by 9s pretty well. So let's see, we have a 12 over 30 reduced by 3s. 4 tenths, so 2/5 is our probability of getting in that area. Okay, so total area is our denominator, and then what area we want to land into is our numerator. Okay, let's look at another one here. Let's see. A target is made of 2 concentric circles. The outer circle has a radius of 12 inches. The inner circle has a radius of 4. What's the probability that a dart will land in the inner circle? So here are our 2 circles. One has a radius of 12 all the way out. The other, this inner circle, has a radius of 4. Well, total area of this is the big circle. which means I'm going to be doing pi r squared. I'm going to leave this in terms of pi. It's actually a lot easier to reduce when we do that. And so I would say my total circle is 12 squared, so 144 pi inches squared. And the inner circle would be 4 squared, so 16 pi inches squared. Okay, from here you can reduce down quite a bit. You can reduce the pi's. Let's say we reduced by 2, so we have 8 over 72, reduce again by 2's, let's say. We have 4 over 36, reduce again, and of course that is 1/9. So we have a 1/9 probability of getting in this small area. But what if somebody said, you know what, I want to know what is the probability of getting in this outside area? Well, you would actually go about it a very similar way. You would say the total area here is 144 pi inches squared. But instead of saying 16 pi inches squared is what we want to land into, we would use the complement of that to say the area on the outside here is 144 minus this inside circle. So 144 pi minus 16 pi will be the area of that outside of the donut. So we would say that's what, 128. Having a hard time doing math in my head today, but that sounds pretty correct. And that is correct. And so we would say, well, that probability of getting on the outside of that, so not in the inner circle, would be 128 pi over 144 pi. Ends up that when you reduce that down, it's just the complement to this. So 8/9 is what you would get. Okay, so depending on what you want, you can end up finding either one, whether it's the inner part that you want or the outer part, by doing just a little bit of subtraction. Okay, a parachutist jumps from a plane. The target area for the landing is a circle with a diameter of 40 meters. If there's one large pond that covers an area with diameter of 10 meters, what's the probability he lands in the water? So basically we're saying there's this big area that he can land in that has a radius of 40 meters. But somewhere in here, let's say it's over here, it doesn't have to be right in the middle, there's a little pond that is 10 meters in radius. Oops, sorry, a diameter of 10 meters. And this is a diameter of 40 meters. Okay, so what's the probability that he lands in the water? Well, let's see. We need to find the area of both of these again. So the area of the big circle is going to be, well, we're not going to use that 40, we're going to use the radius squared. So 20 squared is 400 pi meters squared. And the area that we kind of want to avoid this water, but we're going to see what the probability is he lands in the water, is 5 squared, so our radius squared, so 25 pi meters squared. This will be the probability that he lands in the water. So we reduce down and we divide each of those by 25. We say 1 over 16, I believe, is the probability that we will get, that he will not jump in the water. Okay, or sorry, I said that backwards. 1/16 is the probability that he will actually jump in the water. If we wanted the probability of him not getting in the water, we would use the reverse of that, so 15/16. Okay, so with this, you can do either way, depending on what they're asking, just based on the area of the big one compared to the area of what you want, what you're trying to get with that probability. Let's try again. A town is represented by a circle with a diameter of 50 miles. Okay, diameter of 50 miles. There's a square park with a side length of 5 miles located within the town. All right. What is the probability that a raindrop would land in the town but not in the park? So this is kind of like what we were seeing before. I don't actually want the area of this one to find my probability. I want the area of what's outside of that park. So I still have to find the area of each of those pieces. So for the area of the park, I would be saying, well, 25 squared, so that's my radius squared, is 625 pi, and we're in miles squared. And then I want what is the complement to this 25 square miles that I have here. Well, I would have to find that the rest of the town that doesn't include this park would be 625 pi minus 25 square miles. So we're going to have to do a little bit of multiplication. Do 625 times 3.14. Take a second to pause the video and do that. And you will see that it's actually 1,962.5 square miles. And we're going to take 25 from that because that's the park. So the area that is not the park is 1,937.5 miles squared. 1,937.5 miles squared. Okay, so in order to do this, you can get a decimal for this one because the reducing it is going to be kind of tough, but we can take this 1,937.5 divided by what we got for this 625 pi, so 1,962.5. And when we do that, we see that it's rounded to the nearest hundredth, it's 0.99. So the probability of getting in the town, so this outside area, in the town but not in the park, is a 99% chance. 99% chance, whereas actually getting a raindrop in the park is a 1% chance. Okay, so we use some complements there in order to find those probabilities. Let's do just a couple more. Carnival game has the player release an air-filled balloon towards a square wall. In the middle of the wall is a triangular target. What is the probability that the balloon will not hit the target? So we don't want to be in this triangle, we want to be outside of it. So we're going to have to find the area of that outside part. Well, first of all, we know this is a square, so it's 7 feet by 7 feet. So the total is 49 square feet. Well, let's find the area around this triangle because we want the probability of it not hitting that triangular target. Well, the triangular target, I would find that area by doing base times height divided by 2. Well, base times height, 4 times 3.5 gives us 14, divide by 2, and we see that's 7 feet. So the target is only 7 square feet. Well, if the total thing is 49 square feet, then 49 minus 7 gives me 42 square feet that it could be in. Well, then the probability of the balloon not hitting the target reduced is 6/7. The complement of that 1/7 is the probability that the balloon will hit the target, that it will go in that triangle. All right, rectangle train table is 48 inches by 24 inches. Let's draw that. So 24 inches, 48 inches. The train is only 2 by 6 inches. If an object is dropped on the table, what is the probability that it will not hit the train? So once again, we want the area outside of this train. So let's find the total area of the table by doing 24 by 48 gives us 1,152 square inches. And now we need to find the area that is not the train. Well, this train right here is 12 square inches, which means the area that is around it would be 100 or 1,152 minus 12 square inches. So 1,140 square inches. I'll stop there and allow you to reduce that down. Make sure that you get it completely reduced for that probability. All right, I believe we just have 2 more here and then we'll be done with this lesson. On the front of a tent is a 2-foot square door. The base of the tent is 5 feet and the height is 4 feet. A bird flies at the tent. What is the probability that it does not hit the door? So here is our tent, our triangle, and it has a square door here that is 2 feet by 2 feet. And we know that the base of this tent is 5 feet and the height is 4 feet. So the area of the total front of the tent would be base times height divided by 2, so 10 feet squared. We want to know what the probability is that it does not hit the door, so once again we want the area outside of this door. Well, how big is the door? The door is 4 square feet. So what's left over is 6 square feet, meaning that the probability of getting of the bird not hitting the door is 3/5. 3/5 probability of not hitting the door of the tent. Okay, and last one here. A new school is being built. All students live within a 4-mile radius of the school. Okay, so let's just draw that to begin with. We have a 4-mile radius, which means that here's our school right in the middle. Everybody is within this 4 miles. Okay. The homes are evenly distributed through the area, meaning everybody has an equal chance here. Planners think about students who live within half a mile of the school would walk to school. So here's our half mile. And so those folks are going to walk to school. From 0.5 and 2 miles, they would commute in other ways. So maybe they would ride their bike, maybe they would get a ride with the parent, but all the way up until 2 miles here, so all the way along here is 2 miles. And then from 2 miles to 4 miles, so this outside piece here, I'll make that a little bit clearer. So this outside, oops, let me try that again. This outside piece here is 4 miles. Okay, they would need to ride the school bus. So what is the probability of a student not walking to school? Basically, we're saying I want to know what's the area of this total circle. In this case, we would be doing 16 pi. Okay, you can check my work there. And what's the probability of a student not walking to school? So we don't want this inner circle, but we want everybody around it, okay? Those that maybe get a ride, maybe go on the bus. And so we say that inside circle, what is the area of that? And I would say 0.5 squared pi, which is 0.25 pi. Take that away from 16 pi and you'll have the rest of the district. So 15.75 pi. Well, once you have all of that, you'll need to reduce it down quite a bit. There's lots of ways to do this. I would reduce the pi's and then reduce that 15.75 over 16. Regardless of how you do it, and I'll let you work that out, you get 63 over 64 as our probability, which means it's a pretty good chance that someone is not going to be walking to school, and only 1/64 of the school might be walking to school. So this is how we use geometry and especially areas of our different figures in order to find the probability of certain events happening. I hope this video helps with your homework and for studying.